and ready to jump into advanced topics. So I'm really excited for that opportunity. I am very aware of I'm not aware of all of the things that I don't know. I am cognizant that there is a lot that I don't know. So if you have any ideas or suggestions, please let me know. I'm making this up as I go very quickly in terms of constructing this class. This is something that I care a lot about, and I'm really excited to be here, but it's a work in progress. So please, if you have comments or suggestions, let me know. If there's any problems that I don't foresee coming up, I'm sure I'm going to make lots of mistakes, but I'll keep an open mind. So please give me any feedback that you might have. I'm sure it will be helpful. Okay, so I have a couple of minutes past by my clock, so unless there are any objections, maybe let's go ahead and get started. So let's go back to share screen. All right, you guys are seeing this?
Yes, I am seeing L0 course welcome.
Okay, fantastic. Great, thank you. There's probably a setting on Zoom that I can and should change that will let me continue to see you on my secondary screen while I'm in full screen mode, but I don't have that figured out yet. So for now, I'm just going to take it on faith that you guys are still there, and maybe we'll go ahead and get started. But for this reason, please interrupt me if you have any questions, because I'm not going to be able to see raised hands unless I switch out to full screen or something. Okay, so thank you guys very much. I'm really happy to have you here. So this is Physics 554. I think all of the names on the list are familiar to me, and you're probably all in the right place. So since it's not the first full week of class, is not really the first lecture per se. That's why I'm calling it lecture number 0. About half of what I have to say today is sort of the formalities of going through the class, just to make sure that you and I are on the same page. How to use Canvas, how to find all the course materials, what the heck is going to be going on. And then hopefully for the second half of the class, we'll actually be able to start diving into a little bit of material. And the material that I have in mind, oh wait, I think I do want to be in full screen mode while I want to point. Okay, I think that's better. You guys can see my pointer now, I hope. So, so I guess let's deal with a little bit of the formalities. So I think everybody has seen, hopefully, the materials that I've been posting on Canvas as they become available. So this is sort of the headline for what the class is. You guys are here in the right place at the right time. Some of the information which is actually currently on the screen is already out of date. I posted an update to the syllabus last night that had a few changes in it. One of them is, for example, the classroom that we've been assigned to, even though none of us are in it right now, has changed. So if and when we get to the point that we are back to having in-person classes, it will not be in Gardner 218. I think the new number is 229, but it's in the updated syllabus, so go give it a look. I have now been assigned an official office and an official phone number. Don't go to my office yet. Don't call my phone number yet. I won't see you there, and I won't receive those phone calls. But again, hopefully early October or so, I will be here physically, and you can find me there if need be. Let me point out the office hours. So I'm teaching 2 classes this semester. I've got you guys Tuesday and Thursday mornings, and then there's a block of time in between, and then I teach the undergrad math methods class. So my thought was to schedule the office hours for both classes, more time than is necessary for one of them, but to schedule it Tuesdays and Thursdays in between. So my plan for now is just to create a Zoom room, hang out in the Zoom room, and anyone who wants to come and chat is welcome. I sent an email around just a little bit before class this morning with the Zoom link for the office hours in case you guys want to drop by. In your introductions to me, many people mentioned questions about research, and I'm more than excited to talk about research. So feel free to stop by if you would like to discuss that or any other questions you might have relating to the class. So again, I think most of you got the memo at this point since you're here online and not sitting in Gardner Hall, but we will be beginning the semester at least fully online. And that has nothing to do with COVID, at least not right this moment. This has everything to do with the fact that I am not currently in Las Cruces. I 3 weeks ago was interviewing for this job. 2 weeks ago found out that I got the job and have been rapidly preparing ever since. So I am not in New Mexico, I am in Illinois. And it's going to take me a couple of months to get the relocation of my family lined up. But currently the plan, as filled out in my paperwork through the department, says that I will attempt to be here by Tuesday, October 6th. And that's the plan that I'm going to try and work with so far, no matter what happens with COVID. I don't want to leave this up in the air about whether I'm moving or when I'm moving. I just want to lock something in and get here. So it is entirely possible by that point that the situation on the ground will have changed with regard to COVID-19, and it's entirely possible that the entire university will be online by that point. We will play it by ear. But for now, at least, I know what we're doing. We're going to be meeting online through Zoom in a fashion like this. I will try to come up with a better system for posting recurring Zoom links instead of a brand new link for every class, but I'm still working all of that out. So, okay, what is the class? I refer to the official description in the course catalog. That is what the university expects you to get out of this class with regard to other classes that you might take after this. The list of topics is intimidating, going through wave functions, indeterminacy, the classical limit, of course, the Schrodinger equation, various classic systems that we want to study, including the hydrogen atom. We will spend, hopefully, a great deal of time this semester talking about angular momentum, spin, rotational invariance. I think the second semester we're going to get to things like scattering theory and perturbation theory. So that's a really long list of topics, but on the other hand, we do have a full year together to work through all of this. The course is based for people who are comfortable at the starting graduate level, although you might have some people with different backgrounds. I don't know what courses you might have taken or how long ago you might have taken them, but for the most part, we will assume, comfortable levels of working with classical mechanics and, familiarity at least with some of the conceptual ingredients in quantum mechanics. And we'll be trying to take those ingredients to a much higher level. So since I'm experimenting with everything, can I get the controls back? No, the controls are, no, I have. Okay, so since I'm experimenting with the online technologies, I wanted to test out a Zoom poll real fast. Do you guys have any questions for me before I do? I wanted to try this Zoom poll functionality out with like zero stress to see if it works and to give me a little context for your background. So what I wanted to try was, oops, not this one, but this one. Do you guys see a poll or something that has appeared for you?
Yeah, it just came up.
Okay, cool. So if I set this up right, then this should allow you guys to vote and tell me what experience you guys have in these prereqs or basics. If somebody's missing something, I'd like to know ahead of time so that then I can adjust the course and make sure that I give you the background material that would help. Okay, so it looks like it's working. I can see people voting.
So I came from a different school, so the class numbers are probably going to be slightly different.
Yeah.
What would you say is taught in modern physics? I took a class on Intro to Quantum and a class on Atomic and Nuclear Physics.
I think you've more than
Intro to Quantum.
All right, then yes,
yeah.
I'll take it.
Yeah, so to me, I would consider 451 to be, your senior level mechanics class or your junior level mechanics class at the undergrad level, and this would be the equivalent quantum class, your core quantum class. Cool. Let's see. I've got 15 people in the room, including me. I've got 13 votes. I don't know, maybe I'm miscounting someone or somebody's in the room twice. I'll give another minute in case anybody else wants to vote, and then we'll move on. Okay, so it looks like the voting technology works. Okay, thank you all for voting. I think that's everybody. Cool. So everybody is, so if I click share results, do you guys see this?
Yeah. Yes.
Okay.
Yes. We're a bunch of overachievers.
Yes, excellent. Okay, so everybody is familiar with the basics. That will make my job easier. Cool. So I should go back to sharing screen, sorry. I will probably make lots of mistakes like this, such as assuming my screen is shared when it's not. Please yell at me if I do. Okay, so this is what the official description of the class is. This is my interpretation of what the assignment for me as your instructor is. The main goal, I think, in a year of quantum mechanics is to give you a firm foundation in the mathematics to be able to solve all of the kinds of problems that you will be expected to solve, problems that might appear on your qualifying exam. Quantum mechanics is especially challenging because of the conceptual difficulties. In my mind, quantum mechanics is really a beautiful subject because it's the point that forces us as physicists to take a leap of faith. That's sort of up until quantum mechanics, when you're doing classical mechanics or even E&M, you have a good, well-developed physical intuition for how things are supposed to behave. It's balls rolling down ramps, it's cars colliding together, but you can see it and you have an intuition for it. And the concepts that you build, like energy and momentum and symmetries, are all sort of auxiliary mathematical tools that help you understand something you already have intuition for. And quantum mechanics is very different because you don't have intuition for quantum mechanics. Human beings didn't evolve an understanding or an intuition for quantum mechanics. And this is really the point where balls rolling down ramps doesn't get you very far anymore, but concepts like energy and momentum do. So to me, quantum mechanics has always been very poetic about sort of taking what you understand about the physics concepts of energy and momentum and symmetries, and then taking a leap of faith when energy and momentum and symmetries are the only things that you have to hang your hat on, and you don't have balls rolling down ramps anymore. So one major purpose that I have as we go through the foundations of quantum mechanics is to make sure that we've got a clear conceptual line between sort of what features of classical mechanics still work at the quantum level and which ones don't, and how the ones that don't are broken or modified. Bullet point number 3 is really important to me personally based on my experience as a theorist. There are lots of different ways to study quantum mechanics. I think sort of the simplest conceptually to wrap your head around is something that leans very heavily on wave functions. That's how I first learned quantum mechanics. But unfortunately, that doesn't really set you up for the rest of your career in quantum mechanics and everything you're going to need to do with it, because wave functions aren't particularly helpful for describing things like spin that don't live in spatial dimensions. What's actually a much more solid grounding is an algebraic understanding. So when we go through some of these familiar problems like the harmonic oscillator and the hydrogen atom, I will take an approach which is maybe different than the ones that you've seen in your undergrad classes. I really want to solve these problems algebraically, because the algebras that are satisfied by different quantum operators are the ingredients that carries over and take you up through and including quantum field theory. You want to understand at a very fundamental level how particle physics work. And to me, that's ultimately the point of this course and a whole sequence of courses, is to give you a unified bridge so that you can understand classical mechanics and quantum field theory as all parts of an interconnected whole, that there is a backbone of theoretical physics that takes you all the way from F equals ma to Lagrange's equations of motion to Hamilton's principle of least action to canonical quantization to quantum field theory to the standard model of particle physics. It's all the same thing. And I want to do as much as I can to try and make those connections clear. So to recap, this is what the department says the class is. This is my understanding or interpretation of what the class is. If you guys have any thoughts or feelings about this, please let me know. I am flexible and can adapt the course to whatever serves you guys best. Okay, so logistics. Oh yeah, there's a pandemic going on. So I want to really emphasize the official channels of information and that I trust you to make the best decisions for yourself. And I will make the best decisions I can for this class. And between all of us, we should be able to work this out hopefully with any crazy chaos. So you probably are already aware, 2 important websites that I just want to bring to your attention. ready.nmsu.edu describes the university's official plan. nmsu.edu/coronavirus contains live updates. I strongly encourage you to critically evaluate the plan and the updates. I trust you, like I said, to make decisions for yourself, whatever is best for your health. You take care of you and I will take care of the class. So related to this, the university has asked us to include some very basic checklists that you understand what the plan is and precautions are, and that you agree to the wearing of masks in class and things like that when we are all together. So this is related to a Canvas assignment. If you have any questions on how to find it, please let me know. This is mostly just sort of check the box training to make sure that everyone is on the same page about the plan for the pandemic. So just to make all of this completely explicit, this is ready.nmsu.edu. Important features here include the ability to report the results of your test if you take one and find that you do have coronavirus. They have what they believe is a secure plan for doing contact tracing and letting others know. I am not 100% familiar with the details of how they plan to do this since I just joined and I'm still getting caught up. We can perhaps discuss offline if you have questions or concerns about the plan and how this is supposed to work. I would very much like to know your impressions as students on the ground. As I said, this is nmsu.edu/coronavirus. This is where the university says they will post a communications archive of updates. So they've got tailored information that you can find depending on what your needs are, and supposedly they will post regular updates with news. And I repeated this a couple of times, but just to emphasize it in writing, this class is flexible. Quantum mechanics doesn't change. It is what it is, and we will figure out the best way to study it together. You take care of yourself and your health, and I will take care of the class. Okay, so before I move on to the other details of the class textbook and whatnot, are there any questions, especially relating to the coronavirus protocols? I can't promise that I will have ready answers to all of your questions, but I will do my best. Okay, if there are no questions at this point, then I will move on. So the textbook, I think most of you have taken a look at this in one form or another. The textbook didn't quite play out the way that I thought it would. So the textbook is Principles of Quantum Mechanics by Ramamurthy Shankar. And the textbook is a very nice textbook. It's the one that I used for my graduate quantum. I didn't expect to be using literally the same physical textbook for this class that I had for my graduate quantum class. The second edition is just the edition that I happen to have. So I called up the bookstore and said, I'm teaching this class in 2 weeks. I need a textbook like this, but I don't care what edition you get. So that goes for you guys too. You don't necessarily have to have the second edition. If you have easier access to a different edition, that would be fine. Just keep in mind that the sections might not line up perfectly with the recommended reading that I give you. I'm not going to assign, problem 1.7 out of the textbook. I will write up a file with the problem sets that I would like you to do. I will probably borrow and adapt things from different sources. So I don't think it really matters that you have exactly this textbook. I think it matters that you have Shankar's presentation of how to understand quantum mechanics, which I will follow as closely as possible for the lectures, borrowing sometimes from other sources. But since I'm putting this class together on short notice, I have to rely on Shankar's presentation or organization of the course material very broadly, and then I will jump around and pick and choose chapters, whatever seems useful for our training. So this is the ISBN number for my edition of Shankar, but again, you can get whichever version is most accessible to you. This is a link that tells you how to find the textbook on Amazon. The bookstore tells me that they now have this on order. I guess I don't know if they have physical copies. Has anyone been to the bookstore and obtained a physical copy or tried to obtain a physical copy of the textbook?
See, I did order mine off of Amazon just the other day. It is, oddly enough, the hardcover is cheaper than the paperback, which I don't understand why.
Okay.
That's about $60, I think.
I see. I think Amazon has it used for cheaper than that, but yeah, I don't know. I haven't looked in detail. I didn't know about the paperback versus the hardback. Certainly, I don't care the paperback versus the hardback.
Yeah, I did look at the used. They weren't that cheaper, and they would have gotten here about a month later. So I decided to just get a new one for the next 2 weeks.
Perfect. So also speaking of the next 2 weeks, I had a request for students whose textbooks are in the mail to upload a PDF of the first few sections of Shankar. I have done that. I probably am not allowed to upload large sections of copyrighted material to Canvas, so take advantage of that all you can, and please don't count on me to be able to upload large PDFs of copyrighted material throughout the rest of the semester. But I think the first 6 sections or so that I uploaded here should give you guys a good start while you're waiting for your textbooks to arrive. Okay, the grading scheme is really pretty simple. I'm not going to bother you with things like participation points and quizzes where grad students were above that at this point. The homework is really important. That's where we're going to get most of the practice in. So that's why I chose to weight the homework for the majority of points for the class. For exams, I'm currently planning on having a total of 3. I would like to have 2 midterms spaced out throughout the semester as well as 1 final. If we were doing all of this in class, I would consider doing in-class exams. I would be torn anyway between in-class exams and take-home, but since this is, the era of the pandemic, I think take-home exams are going to be the vehicle no matter what we end up doing. So this is the plan as I have right now. I went with the simplest grading scheme. Honestly, I'm confused about how NMSU classes do their grading schemes. Some classes use the plus-minus system, some classes don't. I don't have any clear guidance about which one I should use. this is sort of the simplest thing, but if you guys feel very strongly that a plus-minus grading system significantly impacts your impact from this class on your GPA, please let me know offline and we can discuss that. I'm not married to the 10-point system. Okay, so this is the tentative schedule as laid out in the syllabus. I would emphasize that this is mostly a wild guess because I know the material in the order that I want to cover it, but I can't judge clearly how long it's going to take. So all of this is going to evolve as we go. Today we're going to do the course overview and a little bit of group theory, hopefully. The first chapter of Shankar is essentially in-depth linear algebra in the notation that we will be using for quantum mechanics. So this is bras and kets and matrix elements and diagonalizing Hamiltonian matrices, all of the machinery that we're going to use. The second unit that we'll go through is a strong review of classical mechanics, especially Lagrangian and then Hamiltonian mechanics. The reason for this is that there is a clear and unambiguous procedure for how to take a theory in classical mechanics when it's formulated in terms of Hamilton's equations and perform canonical quantization, so a standard procedure for how to go from any classical system to the corresponding quantum system. And so we'll try and build up the machinery in classical mechanics to let us precisely describe a classical system that we understand in the right variables so that then we can transition smoothly to the quantum systems. This section on problems in 1D is sort of your typical like particle in a box, free particle, principles of quantum mechanics. This is where we'll try and go over really the conceptual aspects of what does and does not carry over from classical mechanics and work out algebraically some of the simplest problems. The harmonic oscillator is worth several lectures on its own. This is about as much time as I could squeeze into it. We'll see what actually happens at that point in the semester. And then when we finally get out of one dimension and want to start talking about 2 and 3 dimensions, I think that's a great place to talk about rotational symmetry and the generators of angular momentum that work the same way, whether you're talking 2 dimensions or 3 dimensions or 4 dimensions for that matter. And we'll use the group theory a little bit that we're going to talk about today in a more sophisticated way to talk about the 3-dimensional rotation group and how angular momentum operators come out of that. And if that's about as far as I expect to make it this semester, then I think concluding with sin is really a nice capstone for the semester. So that's about as precise as my thinking is right now as far as where we're going to go in the course. I think I have a clear idea of what we're going to do here, a clear idea of what we're going to do here, and then everything else really depends on how much time remains at that point. So I'd like very much to have sort of one midterm on the foundations, the mathematics of the linear algebra that we're going to need, and the principles of classical mechanics. And then midterm number 2, I want to give you opportunities, before the add withdraw date, which is the 16th for the first midterm. The second midterm, I don't know. I could see that going here. I could see that coming after the harmonic oscillator. But that's more or less what I'm aiming for. Do you guys have any questions right now on the timeline, what I'm aiming to cover for the class? Okay, great. So I don't know if you guys are or are not familiar with Canvas. I'm going to assume that you're not because I was not. In my undergrad institution, we used Blackboard. That's also what we used at Ohio State for my graduate courses. Canvas is equivalent, but it has its own format. When you first log into Physics 554 in Canvas, you should see a screen that looks like this. I just want to point out various features. At the time that I took the screenshot, this is what today's module looked like. I created a little module that had all of the links and information that you would need for the first day of class. I will keep adding modules, and hopefully all of that stuff will show up here on the homepage so you can quickly find it. As I add stuff to Canvas, you will get notifications for when announcements are posted, when you have assignments that are due with a certain date, anything like that. And then there are a number of useful links here on the side. I think the most important ones would be the announcements, the assignments. You can look at your own grades. There's a link to the syllabus, and then modules is where I am supposed to upload the majority of the main course files. So I think most of that course information you'll find through modules. And I don't know how you got into Zoom today. You may have clicked the link in the email that I sent you, or you may have gone through Canvas. If you log into Canvas, the link for Zoom is down here at the bottom. If you scroll down, you'll see a button for Zoom, and you can use that to log in for these Zoom meetings. I've tried to post things in a few different places on Canvas as I was exploring how to use it. I have an announcement, for instance, indicating that we are beginning the class online. I'm glad you all got the memo. I posted a discussion board. Many of you already emailed me personally to introduce yourselves, and thank you very much for that. I also have my introduction of myself posted here on the discussion board, and if you would like, you're more than welcome to comment there. If you want to discuss, life in physics, what's it like being a grad student, what's it like being a postdoc after you're a grad student, I'm happy to have those conversations here. Assignments, as I said, you already have your first assignment. This is sort of a trivial assignment from the university just to make sure everyone's on board with the COVID safety plan. You can check your own grades by logging in here. This is the grades of a hypothetical test student when I press the student view button to see what it should look like for you instead of for me. I already mentioned the modules tab. This is what it looks like if you go there directly. If you go to the syllabus tab, it doesn't for some reason display the PDF syllabus. I had to put a link to the PDF syllabus on the syllabus tab, but all of the information should be here in the syllabus. And again, the one that is currently online is version 2, updated a little bit over the one that I originally posted here. Okay, I think that's it for me at the moment. Let me switch out a full screen so I can see your smiling faces for 1 second and ask you guys if you have any questions on the logistics of the course. Stop sharing. Okay. Are we all good on the board?
I've got a quick question about the course overview. So the university provided thing mentioned like perturbation theory and beyond, I guess, but I didn't see that anywhere really explicitly listed on your plan.
Right, so there's no way that I have the time to cover all of that in the first semester. I really want to get into that in the second semester. So let me go back to share screen for 1 second here. But so to answer verbally your question before I do that, the second semester I want to spend a lot of time focusing heavily on perturbation theory and scattering theory. And then whatever menu of special topics we have time for after that. But in my mind, those 2 topics are the main thing for the second semester, and then we'll fit in whatever other interesting things by popular requests or whatever holes in the curriculum I can see. Any other questions, comments? Are you happy with this plan, unhappy with this plan? Anything you want me to know?
I have a question.
Yes, please.
So as far as the homeworks go, would you want us to scan it and send them to you, or do you type it out, or how would that work?
Yes, thank you. So the way that I will probably do most of the homework assignments is I will probably upload my own LaTeX PDF with the problem set written on it. I would like you guys to probably submit back to me some kind of PDF with your answers on it. It's up to you. I don't care terribly much if you write it neatly by hand and then take a picture or scan it, whatever's easiest. If you are proficient in LaTeX, I would love it if you LaTeXed up your assignments and sent them to me. That makes that totally easy to read, and that's good practice for scientific writing, but it's also a lot more time and energy to write them in LaTeX than it is to write them by hand, so I'm not going to require that. That's sort of what I had in mind, that I upload a PDF with the assignment, you guys upload a PDF with the answers, and I grade it all by hand.
Do you want us to upload in Canvas or email you?
Probably in Canvas. I'm going to get so many emails, I will get totally buried and lose them all. But if they're in Canvas, I can't lose them, so that's good. I think I'm familiar enough with Canvas at this point that I can set it up and give you a way to upload the PDFs. This is more for the math methods class than it is for you guys, but obviously, like, showing your work and showing your thought process is the most important thing for me. I care far more about the logic that shows me you understand the math and the physics than I care about the final answer. It's more for the undergrad classes where I have to remind them, like, don't just write down a number for your final answer, show me your logic. You guys are going to do a lot of showing me your logic as you write up the answers. Okay, anything else before we dive into a little bit of group theory? Okay, fantastic. So let me see if I can switch this over. All right, now let me go back to share screen here. And let me hide the annoying one at the bottom. I can still go back and forth. Oh, darn, except I'm not going to want to be in full screen mode. I'm going to want to have the ribbon so I can choose my pen. Okay, I think this is the way that I want it to be so I can draw on the slides. You guys can see this okay?
But there is a technique you can use to open like a pen selection menu in the full screen thing. Not really sure how to do it, but something to look into.
Right, so I know that there's a way when I'm in presenter mode that I can get a simple pen. I can do this, which I think probably works okay, but I've got a lot more pen options if I go out of the full screen. I didn't see a way that I can get access to all those nice draw features. Things like lasso select. I don't think I can draw a circle around this and drag it around.
It's buried somewhere deep in the settings, but it exists.
I wouldn't be surprised. I'll have to go digging. If you have any suggestions, please send me an email or something. That would speed up my ability to find it. Screen. How do I clear the screen? Pointer options. Where's my pen? Pointer options. Why can't I erase all ink on the slide? Okay, I have no idea what happened. So let's just do it this way. Okay, so I mentioned that I might bring in outside sources. I'm going to start off by bringing in one outside source. I don't know if my camera is even still working for you. This is the textbook that I used in my undergraduate abstract algebra class. And the first chapter of Shankar begins with vector spaces, the algebra properties of vector spaces. That's certainly an excellent place to begin talking about quantum mechanics, but it's not the foundation. It's not really the beginning. In my mind, I should start just a little bit early, a little bit earlier than what Shankar does, because the algebraic properties which are possessed by vector spaces are already quite powerful and complex. The algebra properties of vector spaces are, however, built out of more fundamental ingredients called groups. And that seemed like the natural place for me to start. Okay, so abstract algebra is a different way of thinking about algebra. It's a way of thinking about what are the algebraic properties that make up an algebra, and what ingredients do you need to be able to do the usual things that we do with regular algebra. So without trying to give you a formal mathematical definition, let me give you my sort of informal definition, which is that an algebra is just a set of rules that can be used to manipulate both sides of an equality. So, for example, if I start out with y equals mx plus b, regular algebra that we're all familiar with is the set of rules that tells you how to subtract b from both sides, how to divide m from both sides, to algebraically solve the equation given in terms of y to find an expression for x. So this is the usual algebra built out of real or complex numbers under the operations of addition and multiplication, where, of course, subtraction is just the inverse operation to addition, and division is just the inverse operation to multiplication. You're also familiar with a different algebra, which is matrix algebra. It obeys its own algebra, which is different from the usual algebra. Importantly, matrix algebra is non-commutative, such that the product of two matrices AB is not the same thing as the product of the matrices in the other order BA. You can still use matrix algebra to solve the equation y equals mx plus b. I hope this notation is clear to you. I tried to draw the brackets to indicate the shape of the matrix. So this is supposed to indicate that y, x, and b are all column vectors, and the matrix M is a square matrix. So in the same way as before, I can solve this equation. I subtract the column vector b to the left-hand side, and now I need to quote-unquote divide by the matrix M. In matrix multiplication, it matters whether it's on the left side or on the right side. So now you have to think of it as multiplying on the left by the inverse matrix instead of dividing. If you multiply both sides of the equation on the left by n inverse, you cancel n, and you have now successfully solved this equation for x. Different algebra, but same procedure. So the point that I want to make right now to start us off is that there are many algebras. There are, in fact, hierarchies of different kinds of algebras that assume that more or fewer of the usual assumptions about the algebraic properties hold. And you can see this where the usual scalar multiplication, which is called an abelian algebra, is more specialized than matrix algebra, which is non-abelian or non-commutative. So I would say the non-abelian algebra is more general or contains the properties of the abelian algebra. It's just that a non-abelian algebra has an extra degree of freedom. It has the commutator of two matrices, which doesn't have to be zero. And the fact that the commutator is not zero and what you get instead of zero defines the algebraic properties you're talking about. So later on, when we're talking about angular momentum, I just realized I forgot to start recording the Zoom session. I set it all up and I paused it at the beginning. Sorry, let me try to record it now since we're actually talking about physics.
This meeting is being recorded.
Okay, sorry about that, guys. Let's try this again. Okay, so resuming, so we're talking about abstract algebra, the notion that there are hierarchies of algebra, and that in matrix multiplication, the fact that you have a commutator, which doesn't have to be zero, gives you a new ingredient in the algebra. And so what I want to discuss is what kinds of algebras can you have, and what do you gain with the algebraic properties that you add. So the answer for what is the simplest type of algebra, or the minimum ingredients that are necessary to possess an algebra, is called a group. A group is two ingredients. A group is a set of elements, the items like scalars or matrices that you're going to do the algebra on, and you need at least one form of combining them. So the technical term is called a binary operation. You can think of this as just a generalized version of multiplication. You have to define what multiplication of matrices means. And if you have a set like the set of matrices and an operation like multiplication of matrices, then there are four minimum properties that you have to possess to be able to do algebra with that set and with that binary operation. And the four properties are these. So you must have closure. So let's see how this works. It always does this. There. Okay, so you must have closure. Closure is probably the most important one and sort of the first property. If you don't have closure, none of the other ones even make sense. Closure is the statement that if I take two elements A and B, that the product A and B is an element of your group. So if G is the group that you're talking about, you have to start with some element A, which belongs to your group, some element B that belongs to your group, and you have to be guaranteed that any multiplication that you can perform will give you an answer that is also in a group. You can't be able to multiply things and get something outside of the group. That's what closure is. You also have to have associativity. Associativity is one of those basic properties of algebra that we usually take for granted. So this is the statement, x times y times z in this order with the parentheses on the left is the same as the answer if you group the parentheses differently. And in my mind, this is equivalent to saying, I don't have to tell you what the parentheses are. If I have x times y times z, that I get the same answer no matter how I do it. So that a sequence of multiplications is well defined no matter where you put the parentheses. So, okay, closure is important. Associativity we usually take for granted. Identity means that one of the elements of the group must be the identity element. So in the case where your operation is multiplication, the multiplicative identity is 1. What you mean when you say identity is that there's a special element called 1 such that 1 times x equals x. For any x you can define. Right, so for any x, 1 times x gives you x. And 1 doesn't necessarily mean the number 1. 1 means the identity element under whatever operation you're talking about. 1 is the identity if you're talking about multiplication. Keep in mind when we talk about addition that the additive identity is not 1. We'll come back to that in a second. Okay, so that's the identity. And once you have the identity, you can talk about inverses. So similarly, if you have an element x which belongs to the group, if say x is an element of your group G, then you have to be able to find an inverse element x inverse, which also belongs to the group, such that x times x inverse gives you 1, where 1 is the identity. So, okay, we'll talk about all of these properties in more detail in a second. But these are the basic building blocks that are necessary to have an algebra. You have to have at least a set that is closed under your operation. Otherwise, you can't even talk about algebra at all. You have to have associativity. The identity element is critical, and the ability to find inverses is critical. Okay, so these are the basic properties. I'm going to move on and give some examples. Are there any questions at this sort of abstract level? Okay, so let's try a couple examples. So the first one that I want to talk you through is the set of positive real numbers. So I will denote that as R plus. So the set of positive real numbers, and we want to determine, are they a group under multiplication? The operation that I'm specifying is very important. So we want to test all of these properties. How does the logic work? So the first property that I want to test is closure. Closure means if I have two x and y that belong to this set R plus, then the product xy should also belong to the set R plus. In this case, the condition means being positive. So the test of closure is if I start off with two positive numbers, x and y, that are bigger than 0, is the product of two positive numbers a positive number? And the answer is yes. So, sorry, this is the way that I usually talk. In a face-to-face situation, this would work better. But if I asked a leading question like that, please, anybody feel free to jump in and just give me the answer. Okay, so this is how we see that the positive real numbers are closed under multiplication. The identity element is also an element of the set, right? So the multiplicative identity, the identity under this operation, is 1. And since 1 is a positive number, the identity element is included. Associativity we basically get for free. Regular algebra is associative, so the algebra of positive numbers is also associative. The only one that you need to think a little bit carefully about are the inverses. These are, again, the multiplicative inverses. And so if x is some positive number that belongs to my group, then the multiplicative inverse is 1 over x. And the question is, if x is a positive number, is 1 over x a positive number? And the answer is yes, as long as it is strictly positive. So this is the case where you have to be a little bit careful. If I didn't pay attention to 0, I could have missed that, and I would end up with something that is not a group. Right? So this is the set of elements who are greater than 0. If instead I had written x greater than or equal to 0, and I had included 0 in the set, closure would be fine, identity would be fine, associativity would be fine, but I would fail the test of inverses, because 1 over 0 is not a positive number. Or 1 over 0 is not a number that belongs to the set. Any questions on this example? If no questions on this example, let's try a couple more. So now I want to try out the poll functionality again. I think it's working so far, but I want you to vote and tell me whether you think the even integers, sometimes written as 2z, where z are the regular integers, form a group under addition. Note here that the operation is addition and not multiplication. So when you think about identity and inverses, keep in mind we're talking now about the additive identity and additive inverses, not multiplicative ones. And similarly, the question, are the odd integers a group under addition? So let me attempt to start the poll.
So Z is all positive and negative integers, right?
That's right. So this is all positive, negative, and 0 integers. Even integers, this notation means if you took any integer and you multiplied it by 2, then you get an even integer. This means you take any regular integer, multiply it by 2, and add 1, you get all odd integers. Okay, so take a few minutes and think this through for yourself, and then we'll go through the tests together. These are the 4 properties that the group must satisfy in order to be a group. So as you guys are voting, does it show you how people are voting, or do only I see people as they are voting in real time?
Only you.
Okay.
Yeah, we don't see any results.
Okay, until I hit post. Okay, I've got 11 out of 14 people who voted. I think the 14 does not include myself. So I'll give you guys a couple more minutes to think this through. Okay, looks like everybody has voted, so I will end polling and show the results. Okay, so we have a bit of a split. So 11 versus 3 say that the even integers are a group under addition. So you're still seeing my screen, correct? Including
I'm seeing a friend is playing a game on the computer.
Yes, I'm gonna have to figure out how to manage all those pop-ups so you don't see everything that people comment on my Facebook and every time a friend starts playing a video game. Okay, so are the even integers a group under addition? Let's work out the properties. So the first one is closure. Closure. All right, let me see if I can lean this down for it. So if I take two even numbers and I add them together, do I get an even number as the answer?
Yes.
Yes. So how would I show this if I asked this on a homework problem? I would say consider one even number. Let's call it, let's say, I don't know, Z1, and I'll call it, I don't know, 2 times n, where n is an integer. So just for the sake of having a name, if n is an integer, 2n is some even number. Let me even maybe call this E1 for even number number 1. E2, even number number 2 is 2 times m for some m, which is also an element of the integers. And so the proof would be that if I have E1 plus E2, that this is equal to 2 times n plus 2 times n. And if you factor out the 2, then this is 2 times an integer. And so this is now another even number, and therefore you know it's an element of the set of even numbers 2z. So yes, the even integers are closed under addition. Do they contain the identity element?
Yes.
Yes. What is the identity element?
0.
For addition.
0.
Yes, for addition is 0.
Exactly. So that's the critical trick here. The additive identity is 0, and since 0 is an even number, it is included. Associativity, again, you basically inherit for free from ordinary algebra. What about inverses? Are the inverses of even numbers included in the group?
No.
Yeah.
I hear yes and I hear no.
Well,
So again, go ahead.
Well, I was just saying, so for addition, the inverse would simply be the subtraction, right?
Yes, exactly.
Yeah.
So that's the critical step, is recognizing that since we're talking about addition, the inverses are not multiplicative inverses, they are additive inverses. So we're talking about if there is an even number e equal to 2m, then can I find E inverse such that E plus E inverse equals the additive identity, which is equal to 0. So E inverse equals minus 2m, and the proof, such as it is, would be that this is equal to 2 times minus m. Minus m is an integer, so this is equal to, if you like, E2, and this is an element of 2z. So you would get a different answer if you were thinking about multiplicative inverses. If 2 is an even number 1/2, its multiplicative inverse is not. But if you're talking about addition, yes, it is satisfied. So the answer is yes, the even numbers are a full group under addition. Any questions on that? Okay, by the same reasoning, you will quickly find, so let me write, the answer is yes for the case of the even integers. The answer is no for the case of the odd integers. Can someone tell me which of the properties are violated by the odd integers under addition?
Closure.
And identity.
Closure is violated and identity is violated. You're right, they are both violated. So closure is violated because 1 plus 1 equals 2. I hope we all agree on that. Odd number plus odd number gives you an even number. So closure is violated. And identity is also violated. Because again, we're talking about the additive identity 0. 0 is not an element of 2z plus 1, even though the multiplicative identity 1 is. Here we're not talking about multiplication. Okay, any questions about this? Is everyone okay with how this logic works? Okay, I see 10:52 by my clock, so I think we've got another almost 20 minutes. No, 25 minutes, excuse me. All right, so now I want to talk about a couple of very important groups. These are groups that are very important in particle physics and in physics in general. The group that I want to talk about first is called U1. U1 stands for the unitary group in one dimension. In general, if you're talking about U2 or U3 or UN, these things are matrices, and n tells you the dimension of the matrix. If n is equal to 1, you don't even have a matrix, you just have a number. So for those who are familiar, unitary is a condition that applies to matrices. If I have a one-dimensional matrix which is unitary, that's really simple. It just means that that number is e to the I theta. It's a pure complex space. So I'm assuming everyone is familiar with Euler's law, how to write down complex numbers in this form. If you are not, please send me a private message and we can discuss. Right, so this is the set of complex numbers. In general, you may recall a complex number can always be written in the form z equals r e to the I theta, where r is equal to the complex magnitude or the modulus of the complex number. So the group U1 contains all complex numbers whose magnitude is equal to 1. And that's what's being shown here. So if I draw a plot of the complex plane, so I have the real part of the complex number z on the x-axis, the imaginary part of the complex number z along the y-axis. If the magnitude of the complex number is 1, then that defines a circle of radius 1 centered on the origin. And every point on that circle can be written as z equals e to the I theta, where theta is just the rotation angle relative to the positive real axis. So most of this is probably familiar to you, although maybe you've never called this U1. Let me emphasize that U1 plays a fundamental role in physics. Understanding what I mean by this statement will require a lot of extra explanation, but let me tell you directly that U1 is the fundamental symmetry of nature associated with electromagnetism. That you can start with a non-interacting Hamiltonian that has just, it just has electrons that fly through free space and they don't emit any electromagnetic fields at all. Starting with that starting point of free electrons plus the group properties of U1 symmetry uniquely predicts Maxwell's equations. This is an unbelievable statement that I could not wrap my head around the first time I took quantum field theory as a graduate student, but it's true. That the group algebra of U1 can be uniquely associated with the physical properties of Maxwell's equations. So we will come back to this group many times, and you will come back to it in a big way in quantum field theory when you show how the use of this group symmetry leads directly to Maxwell's equations. But that this is not just a random group that I made up. This is one of the most important groups in physics because it is associated with electromagnetism. Okay, so let's take some time in class and let's work out together, if at all possible, the proof that U1 is a unitary group. I would really like to be able to see everybody's faces while we're doing this.
I think there is some way to have all the participants' cameras be put into a separate window. I'm not sure how, though.
Yeah, that's what I'm looking for. Optimize screen sharing for video clip. If I share that one. Okay, I'll have to figure that out on my own time. I'm sorry, I'm just going to have to stare blankly at you right now. Okay, so let's walk through this. So first, let's establish closure. Please, anybody and everybody, feel free to take your microphones off mute and just let's have a conversation. Let's walk through this. What do I need to show for closure? Who can tell me?
Well, you take two different angles that are real, and you take Z1 and Z2, you multiply them, and you see whether the product gives you an angle theta that belongs to R, which it does.
Excellent, beautifully said.
Wait, so we're proving that it's a group under multiplication, you said?
Yes, sorry, thank you, I didn't specify. This is a group under multiplication. Good call. Under multiplication. Yeah, so that's exactly right. I can't tell who gave me the answer, but that is exactly the correct answer. I want to take two arbitrary elements of the group. So take some Z1 and Z2, Z1 comma Z2, which are elements of U1, and I want to show that Z1 times Z2 is an element of U1, which means it can be written in this form. Or in other words, this thing must be expressible in the form e to the I something. And if I can find what that something is, then I have shown that the product is of this form, and therefore it's an element of the group. And so once you know mathematically what you're supposed to show, it follows in 2 seconds that Z1 times Z2 is e to the I theta 1, e to the I theta 2, and by regular algebra, this is e to the I theta 1 plus theta 2. And theta 1 plus theta 2 is the new angle theta, so this is in fact an element of U1. So yes, we have proven a closure. The formal mathematical notation would be to say that for any Z1 and Z2 who are elements of U1, the product Z1 times Z2 is also an element of U1. QED. Okay, so that's closure. Associativity we get for free. I'm not going to worry too much about that. Let me also maybe point out one useful thing about this exercise. So in computing this, we've actually computed more than just showing that the group satisfies closure. We've constructed sort of the arithmetic rule for how elements of this group combine. So if instead of calling them Z1 and Z2, I could have called them, let's say, Z of theta, defined to be e to the I theta, then what we've shown is that Z of theta 1 times Z of theta 2 is equal to Z of theta 1 plus theta 2. And that sort of group arithmetic rule can be used to derive the rest of these properties. All right, so now let me see if I can delete all of that stuff without deleting my text. Excellent. Okay. So we've seen closure, we've seen associativity. What about identity?
For theta equals 0, you get the identity element.
Beautiful. So because theta equals 0 corresponds to Z of theta equals e to the I 0 equals 1, and 1 is the multiplicative identity. 1 is an element of U1, and therefore, yes, it satisfies identity. And inverses are also very straightforward. If I have Z equals e to the I theta is some arbitrary element of U1, then what is Z inverse?
E to the I minus theta.
E to the minus I theta, very good. Because Z times Z inverse equals e to the I theta times e to the minus I theta equals 1, and 1 is the multiplicative inverse. So yes, in this way we show that all 4 properties are satisfied by U1, and U1 is a closed group under multiplication. Any questions on this exercise? Okay, great. Now let's do one that's slightly less trivial. The next group that I want to talk about is SO2. So the 2 means that I'm talking about 2 by 2 matrices. The S and the O stand for matrix properties that are called special and orthogonal, if those mean anything to you. So this is the special orthogonal group.
Could people mute, because I'm hearing a lot of like paper stuff instead of the teacher?
Yeah, thank you for that, Exie. Okay, right. So these are 2 by 2 matrices, and in general, so these 2 by 2 matrices are rotation matrices. So this is the 2-dimensional rotation group. And as you've shown in your other classes, I expect 2 by 2 rotation matrices can be written in general in the form cosine theta, sine theta, negative sine theta, cosine theta for any real angle theta. This is equivalent to the algebraic properties that are being specified here. Special refers to the determinant. The determinant of this matrix is cosine squared plus sine squared equals 1. Special means that these are 2 by 2 matrices whose determinant is equal to 1. And orthogonal means that the matrix's inverse is obtained by transposition. So these 2 properties are not super important for the discussion that I'm having right now. I'm just giving it for your information. So this property is what orthogonality means, that the transpose of the matrix basically takes that minus sign and moves it over there. And that is equivalent to inverting the matrix. So because these correspond to rotations, this is a 2-dimensional coordinate transformation that takes me from, say, my regular Cartesian coordinates x, y, and then it rotates my coordinate basis so that my new unit vectors, say I hat and j hat prime, are now rotated by some angle theta. And this matrix is giving you the x and y projections, cosine sine of the new rotated I hat, and then negative sine, cosine are the xy components of the new j hat. So this corresponds to these rotations. In terms of applications to fundamental particle physics, SO2 is not the most important group. Its close complex cousin, however, SU2 is. If I take these matrices and allow the elements to be complex, then instead of orthogonal, the matrices are called unitary. And the special unitary group in 2 dimensions is, again, a fundamental symmetry of physics. In 2 dimensions, that 2-dimensional rotation corresponds to the origin of the weak nuclear force, where there are 2 different kinds of particles. And these SU2 rotation matrices are basically rotating between, say, an up quark and a down quark. They're rotating between an electron and an electron neutrino. And if I take this one step further and I can imagine 3-dimensional rotation matrices, SU3, where the matrices can be complex, is the origin of the strong nuclear force. This is the fundamental gauge symmetry that lets you take a free, non-interacting theory and uniquely write down the Hamiltonian or the Lagrangian associated with the strong nuclear force. So all of these group elements are absolutely fundamentally important in particle physics, which is why I think it's worth spending so much time on it. Okay, so now I want to work through the similar exercise for SO2. The algebra here is going to be a little bit more involved because we'll need to use some trig identities, but the idea is the same. So you guys, please walk me through the proof that SO2 is a group. If I want to establish closure, what do I need to show?
Take 2 different angles and take the product of the matrices.
Yes. So show that R of theta 1 times R of theta 2 can be written in the form that looks like R of theta 3 for some theta 3. And find what it is. So we need to show that if I have one matrix, which is cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1, and I multiply that by a similar matrix, cosine theta 2, sine theta 2. Sorry if the handwriting is poor here. Let me zoom in and see if that helps. Minus sine theta 2, cosine theta 2. I need to multiply those 2 matrices and see what I get. So it's going to be a big answer. Walk me through. For the first element, what do I get? I multiply this row and this column.
Cosine of 1 plus theta 2.
Theta 2.
Very good. Cosine theta 1, cosine theta 2, and then minus sine theta 1, sine theta 2. I heard that someone is already thinking about trig identities, so maybe let's write that in parallel as we go. What is this combination of functions equal to?
Cosine theta plus 1.
Yes, exactly. Okay, so I can see that the everybody answer at the same time on Zoom is not going to work so well. Maybe I'll have to come up with a better way for that. Let's go with it for now while I think of alternatives. Okay, great. And so similarly, we fill out the rest of the matrix. So if I multiply the other elements, I get, let's say, cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. That combination happens to be exactly equal to sine theta 1 plus theta 2. And by the magic of algebra, if I keep working out the rest of this, I get negative sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. This is exactly equal to this one up to a minus sign. So this is negative sine theta 1 plus theta 2. And again, the other element works out to be cosine theta 1 plus theta 2. Okay, and so by multiplying this out, we prove closure and we obtain for free the group arithmetic law, R of theta 1 times R of theta 2 equals R of theta 1 plus theta 2. And since there exists some theta 3 that we were able to find that satisfies this, we have proven closure. One thing that's interesting to point out is that this group arithmetic law is identical to the group arithmetic law that we wrote down for U1. So this was, no, please, no command prompt. SO2, and this is U1. We had Z of theta 1 times Z of theta 2 equals Z of theta 1 plus theta 2. And in fact, the fact that the group arithmetic laws are the same is telling us actually that these two groups are the same group. That the group algebra is in fact identical, even though the groups themselves look totally different, right? These are 2 by 2 matrices. This is just a complex number, but the algebra of how this group behaves is identical to the algebra of how this group behaves. And so one can prove, in fact, that these two groups are isomorphic to each other, meaning that their algebra is identical. Okay, so closure was probably the hardest part, or the longest part of the exercise. None of this is terribly hard. From that, we need to show the rest of the properties. So associativity, we inherit it for free, but now it's also trivial to show by using the group arithmetic law. If I have R of theta 1 times R of theta 2 times R of theta 3, my group law tells me how to combine them. R of theta 1 times R of theta 2 is R of theta 1 plus theta 2 times R of theta 3. And so this is just R of theta 1 plus theta 2 plus theta 3. And you get the same answer if you put the brackets the other way. Identity. So one can immediately see, of course, that the identity matrix, keep in mind that this is the identity element for our matrix multiplication under which the group is defined, that this can be written as R of theta equal to 0. Cosine 0, sine 0, negative sine 0, cosine 0. So yes, the identity element is an element of the group. And inverses would be a real pain to prove using direct matrix multiplication. They're real straightforward to use to show, however, using the group law. If I want R of theta times R inverse of theta equals the identity matrix, which we already said is R of 0, I want to find some group element that can act as the inverse. We already know that since this is equal to R of, let me write this as, say, R of theta 2, if this was theta 1, then this is R of theta 1 plus theta 2. And if my identity element is theta 1 plus theta 2 equals 0, then that again immediately gives me, by algebra reasoning, that R inverse of theta must equal are of negative theta. And again, this is an element of SO2. And so that completes the proof that SO2 is a number. Any questions? Okay, so we're out of time for the class, which is good. I just had a couple of closing remarks. The point about constructing group theory is that the group laws themselves are sufficient to do algebra with. If I write down a messy expression for some unknown group, G, all I need are the basic algebraic properties of a group to solve this equation for G1. You can regroup the parentheses, you can use inverses to get the identity element, and use the definition of the identity element, and so on and so forth. But the algebra of the group is completely self-contained, and you can use it to solve things algebraically. Why is this important? Well, some groups are discrete. A simple example is the subgroup of 90-degree rotation. So this is a subgroup of SO2. If I consider only rotations by 90-degree intervals, so rotation by 0, rotation by pi over 2, rotation by pi, rotation by 3 pi over 2, these four elements by themselves also form a closed group under matrix multiplication. It's just discrete. There are exactly four elements. Whereas on the other hand, the specific groups that we just talked about, U1 and SO2, are continuous. They have an infinite number of elements, R of theta and Z of theta, and their dependence on that parameter theta can't be arbitrary. It has to be smooth. It's smooth, and in particular, it's differentiable. There are many groups of this type, and they play a very important role in quantum mechanics. These groups are called Lie groups. It looks like it's spelled lie, but it's not a lie, it's the truth. These are Lie groups, and they are deeply connected to symmetries, quantum symmetries, and the way that you implement symmetry conditions in quantum mechanics. So the fundamental symmetries in physics associated with translation symmetry, rotation symmetry. When you talk about special relativity, you'll talk about Lorentz symmetry. And then when you talk about interacting theories, you'll talk about gauge symmetries. All of these fundamental symmetries are associated with specific Lie groups. And the algebra of those specific Lie groups, of which U1 and SO2 are specific examples, determine all of the consequences that symmetries have in physics. So that's the point of starting off this. And I hope that discussing groups now will position us well next time to generalize beyond just one operation, like multiplication, to two operations, addition and multiplication. And those ingredients will take us out of groups and into fields. And that includes vector spaces, which are a vector field. So next time we will pick up with chapter 1 in Shankar. And my hope is to put together a problem set for you over the weekend and maybe post it online on Monday. We'll see if I get there. Any questions for me? Let me look back at faces instead of my own words. So I am available to you guys. Please feel free to reach out if you have questions. I have office hours, like I said earlier, scheduled in 15 minutes. I sent around the Zoom link. Any of you are welcome to join. We can chat about questions you have for the class. Any other questions you want to talk about. If you're interested in research, I have some slides I'd be happy to share with you. Anything else that you guys have for me? Okay, if not, then thank you all for your time, and I look forward to the semester with you.
Thank you so much.
Have a great weekend.
See you Tuesday.
Thank you.
Thank you.
Thanks, guys.
Thank you.
Do you have a moment?
Yeah, absolutely. Feel free to stay on.
Okay.